Welcome to the Explainer. Today, we are pulling back the curtain on the fundamental building blocks of all software. We're talking about the hidden logic, the very blueprint that makes our entire digital world tick. I mean, really think about that. How does your map app find the fastest route in the blink of an eye? Well, the answer lies in two core concepts that power pretty much everything: data structures and algorithms. They're the secret sauce, and today, we're going to dive right in. So here's our game plan. We're going to start with the problem itself, just a mess of digital chaos. And then, piece by piece, we'll build our way up to the really clever strategies that software uses to solve it all. Okay, so every single great piece of software, it all starts with the same raw material: data. And you know what? At the beginning, it's usually just a complete mess. I mean, look at this. This is what we mean by raw data, just a jumble of words. Now, if I asked you to tell me the most popular sport here, you could do it, right? But you'd have to scan everything, count it up. You might even make a mistake. Now, just imagine a computer trying to do that a million times a second. That's the chaos that developers have to solve. But check out what happens with just a tiny bit of structure. All of a sudden, the answer is instantly clear. Cricket is the winner. This simple transformation right here from chaos to clarity, this is the first, most fundamental step in building any piece of powerful software.
And the benefits? They're huge. We save time, we get rid of mistakes, and we make the information so much easier to work with and understand. So the big question is, how do we create this kind of organization inside a computer's memory?
Well, that brings us to the idea of data structures. The best way to think about them is like specialized filing cabinets for our digital information. Each one is designed for a very specific kind of job. They literally give our data shape and form. You see, the core idea here is really simple. It's not just about storing data. It's about storing it in a way that makes it super fast and easy to use later on. It's all about being smart today to save a ton of time tomorrow. Let's compare two of the most fundamental structures out there. First, you've got an array. Think of it like a numbered row of filing cabinets, all sitting right next to each other in memory. This makes it incredibly fast to grab any file if you know its number, but it's pretty rigid. A linked list, on the other hand, is more like a chain. Each link holds a piece of data and then points to the next link in the chain. It's super flexible for adding or removing links, but to find a specific one, you have to start at the very beginning and follow the chain all the way down. Now let's talk about some more specialized tools. You ever wonder how the undo function works in your text editor? It uses a stock. The last thing you typed is the very first thing to get undone, just like taking the top plate off a stack of dishes. Last one in is the first one out. Simple as that. And its cousin, the queue, works exactly like any line you've ever stood in. First in, first out. The first person who gets in line is the first person who gets served. This is precisely how a printer handles print jobs in order, or how Spotify manages your playlist of upcoming songs. Okay, so we've organized all our data into these neat little structures. That's great. But now we need a set of instructions for actually doing something with it. And that, my friends, is where algorithms come in. An algorithm is, quite simply, a recipe. That's it. It's the step-by-step instructions that tell the computer exactly what to do with the data we've so carefully organized. It's the action plan. And these recipes, they're designed to do all the crucial things we need. Things like searching for a name in your contacts, sorting your emails by date, or inserting a new appointment into your calendar. But here's the catch. There are often multiple different recipes to solve the exact same problem. So how in the world do we know which one is the best? Well, we have to look at the scorecard. We measure an algorithm's performance with something called complexity. Now, this isn't about how hard the code is to read, it's about how well it performs when the amount of data gets bigger and bigger. You know, will your app still be fast with a billion users, or is it going to grind to a halt? That's the question complexity answers. To talk about this, engineers use a kind of shorthand, and the most important one by far is called Big O notation. All you really need to know is that Big O describes the worst-case scenario. It answers the question, when things get really, really bad and the data is massive, just how slow is this thing going to get? See, planning for the worst case is how you build reliable software that doesn't crash under pressure. All right, so now we have our tools and our scorecard. Let's look at a couple of really clever strategies that algorithms use to solve problems efficiently. First up is something called the greedy algorithm. And it's a very intuitive approach. At every single step, it just makes the choice that looks like the best one right now, without worrying at all about the long-term consequences. It's simple, it's direct, and a lot of the time it's surprisingly effective.
So, say you need to make change for $18. The greedy approach just repeatedly takes the largest coin it can. It grabs a $5 coin, then another, then another. Okay, now we're at $15. Another 5 is too big, so it greedily grabs the next biggest thing, a $2 coin. We're at 17. Finally, it takes a $1 coin to hit the target. It's simple, and what do you know? In this case, it actually found the perfect solution.
Another classic strategy is divide and conquer, and the logic here is really simple. If a problem is too big to solve, just break it into smaller, identical little subproblems. Solve each one of those small pieces on its own, and then at the end, combine all those solutions to solve the original massive puzzle. So from messy list to these really elegant solutions, data structures and algorithms are truly the silent architects of our technology. They are the fundamental logic that transforms raw, messy data into the seamless, instantaneous experiences that define our digital lives. So the real question is, now that you know the tools, what will you build with them?